Hello everyone, in this video I'm gonna give you some background information about concrete damage plasticity or CDP model. So what is a concrete damage plasticity CDP? The model is a continuum plasticity based damage model for a concrete, and it assumes that the main two failure mechanisms are tensile cracking and compressive crushing of the concrete material. So as you can see, we have a stress strain curve, and we have a tension in the positive part and the compression in the negative part. So normally where the compressive stress is always bigger than the tensile one, and this is because of the behavior of concrete material, that they have a good compressive behavior, but they don't really have a good tension behavior. So we call this the elastic part, the linear part, the elastic stiffness, which is the undamaged part. And under a uniaxial tension, the stress response follows a linear elastic relationship until the value of the stress of the failure stress when we reach to this part. And after that, the softening part happen, that we show that with a scalar stiffness degradation. So as you can see here, we have 1 minus dt, and this value here is the damage parameter. So once the damage parameter reaches to 1, we have a full failure in concrete. And also this softening part also represents macro cracking in the concrete material. Also, under uniaxial compression, the response is linear until the value of the initial yield, which is here. And in elastic, in the plastic regime, the response is typically characterized by the stress hardening, followed by a stress softening beyond the ultimate stress, which is this point. So normally, in total, the damage plasticity continuum model was based on the following stress-strain relationship. So we combine the compression and tension, and also the total strain tensor is going to be like this. So what do we need as the input for a concrete material? So as you can see, if I add a concrete damage plasticity, I would have the compressive behavior, and I'm going to have a tensile behavior. And also from the sub option, I can add the damage parameter and in elastic strain, and here damage parameter and cracking strain. So I've provided you the Excel file that has the some concrete material property. For instance, this is a class B that I'm going to use for the most of the tutorials in this course. And also I also provided you the class B30, class B20, and also the references here, that if you want to use them, you can reference to this one. So as you can see here, we have a compressive behavior that, for instance, the yield stress is around 10.2, and also compressive damage, which goes up to 0.81. And also same thing for the tensile behavior. For instance, this one is the better one. We have more data here, which starts from 2, and it goes up, and as you can see, it goes to around 0 here. So now this is how to define a compressive behavior and tensile behavior. Also, we have the plasticity, which we use the flow rules. The plastic damage model assumes a non-associated potential flow, which means that the yield functionality and the plastic potential doesn't occur at the same time, so they are not perpendicular to each other. And the flow potential G chosen for this model is the Drucker-Prager hyperbolic function. So as you can see, we're going to use this formula. All these data comes from the Abacus help. So what we have a dilation angle. The angle of dilation control an amount of the plastic volumetric strain developed during plastic shearing, and it assumed a constant during plastic yielding. And also this is in a PQ plane, which is the horizontal axis P indicate the mean stress, while the vertical axis Q indicate deviatoric stress. Then we have eccentricity, which is a flow potential eccentricity. And this is a very small value. The default value is 0.1, but for instance, for one of these concrete, for instance B50, we use 1. And then we have this parameter, which is the ratio of initial biaxial compressive yield stress to the initial uniaxial compressive yield stress. And again, the default value is 1.16, and K is the ratio of the second stress invariant on the tensile and to that of on the compressive one. So for this one, this value, there is a condition that this value should satisfy this one, which should be between 0.1 and 1. Normally, in the most of the work that I've checked, this value is 0.667. And also viscosity parameter, that you only need to provide this when you use a static solver. You don't need this value for the explicit one. And normally we consider this very small value. So how to find this parameter? I found some good work in literature that you can download this file from the is in a PDF format, and you can use these reference. For instance, to find this parameter based on the first work, they recommended that you need to do the uniaxial compression, uniaxial tension, the biaxial failure in a plane state of stress, and triaxial test of concrete. And with these tests, you can find these parameters that you can, as you can see here, Young modulus, the angles, and also compressive behavior and tensile behavior. However, I found another work which is a simplified CDP model, and which published in 2017. They introduced the method that you don't have to do the test, and you can just use the theory to find those values. So you can check out these works, and probably you can find a way how to obtain these input value for your concrete. So that's everything for the theory of the CDP model that I'm going to use in the future tutorial. I hope to see you in the next tutorial. Thank you.